Today is pretty much going to be covering Python within Itasca software itself. We're going to start off by going over kind of what's available within the software for Python. How do you actually open and run Python files? Then we're going to be covering kind of the differences between Fish and Python. What's the similarities and kind of what's the preference to using Python? We're then going to start to cover the Itasca Module, which is the main package which provides connectivity towards the into Itasca software. Then we're going to cover the difference between the two main interfaces, which are kind of the ways you can interact with the Itasca module, and then cover kind of some examples and some code snippets so as to how to go over them. So starting off with Python in the actual Itasca software, how do you access, run Python code, and what's the capabilities of it? Python is available within FLAC3D, 3DEC, and PFC. And it's Python version 3, and there are natively installed several libraries such as NumPy, SciPy, and PySide. To actually run and use Python within the software, the main connectivity through that is the IPython console. Now, this is a Python console similar to the one in idle, which allows you to just kind of quickly run some Python code or some snippets, but doesn't actually provide any way to kind of save your Python code within the memory itself. So in this example, the Python console here is just highlighted in pink so as to kind of denotate where it is. And by default, this might not be open within your software. And so in order to do that, in the toolbar, there's a Python dropdown. And if you select that, you can then select the IPython console, which then opens up the console for you to interact with. Now, in terms of actually running Python scripts within the software, Python scripts can be loaded in as data files, the exact same as Fish scripts. So in this case, the pink highlighting is highlighting the Python files, and the light blue teal is highlighting the Fish files. You can see that the Python script editor, which opens up within the software, is pretty much the exact same as the Fish editor. There's no real visual differences or any differences when you're running the code, except that there's a slight different background color so as to help denote whether you're looking at a Python script or a Fish script. Now, Python scripts can be run within the software in the exact same way as a Fish script. So by pressing the green run button at the top of your toolbar. This will execute all the code within your Python script and run it. And one final thing to kind of denote is that Python scripts, when you use the print function, don't actually output to the console like the Fish functions do with io.out. Python scripts instead output to the IPython console. Now, just to give kind of a general example of what it looks like when using Python within the software, I'm just going to go over a quick example, which shows how you can use Python to map pore pressure point clouds to grid points. There's kind of a bunch of Python code here, which initially right now you don't really have to understand. This is simply to serve as a demonstration of using Python within the software. Later on, we're going to be going over how the code syntax within Python for the software actually works. And hopefully by the end, then you'll be able to, we'll come back to this and you'll be able to look at it and understand more really how it works. But basically, all this is doing is it's loading in some pore pressure point data, and it's then using that point cloud and mapping it to grid points. So coming back to our plot then, we can see that the loaded in pore pressure points just simply resemble a cube structure. And by the Python code, we're then able to map those pore pressures into zones and grid points. Going back to the code, we can see that this is pretty much it's all the mathematics are simply done via one single function imported from SciPy's interpolate submodule. And this just kind of is one of the main powers of Python in that you're able to use external libraries in order to quickly do simple calculations. So once again, just to highlight, this Python script itself is opened in a code editor, very similar in style to the Fish code editor, and running the script is simply done by pressing the green run button at the top. What are then the kind of primary differences within the fish and Python languages itself. And kind of the chief thing with that is, why should you, as engineers and as programmers, bother using Python instead of fish? Well, firstly, Python is capable of doing everything that fish can do, with some temporary limitations. That's the little asterisks that I'll discuss later. In addition, the Python standard libraries are incredibly powerful and allow you to do all sorts of different string manipulation, access to data structures, and mathematical processing. And this is then further extended by the additional features from SciPy and NumPy available within the Itasca software, allowing everything from numerical integration to linear algebra and eigensystems and so forth. However, the main reason why it's preferential to use Python instead of fish is for speed. In terms of doing numerical computations or variations of your model, Python can be extremely faster than fish. So this table right here is just some standard times, which was created by Jason actually, measuring the times that it took in order to do some methodologies with fish, then with kind of basic Python bindings, and then via optimizing this with NumPy within Python. And you can see that for something as simple as looping through all the zones in a model and performing either some calculation from a resulting value of those loops or setting a new value within those loops, using NumPy bindings within Python can allow for extremely faster times, up to 34 times faster calculations. So another really powerful thing about the Python interpreter is its save and restore functionality. Within Itasca software, when you either create a new model or restore an old one, the fish interpreter is reset to that old state. However, with Python, the entire Python state can be detached from the actual model, which means then that Python variables and functions aren't reset and aren't saved in the whole save file. And this can be the entire Python state or only certain variables and functions. Now, the power in of this is that it allows Python to act as kind of a higher power. So this allows you to detach any object type within Python. So this includes things such as just generic data structures, all the way to custom classes that you can define. It also allows you to execute functions independent of the state of the model. So kind of an example of this use would be to, say, create a Python function which varies input parameters and runs for some large amount of models, and then takes the resulting values and can optimize the results via SciPy optimization algorithms. So kind of coming back to that asterisk though, there are some factors which Python is lacking or is missing in comparison to fish. Now, the main thing to note with these limitations though is that they are temporary. The plan is to have full parity between Python and fish within FLAC3D, 3DEC, and PFC version 8. The first things that Python is missing is it's missing zone field data function, as well as geometry logical functions. There's also some things which you can currently do within fish, but not within Python. Chiefly, you can't set or see the history of a Python variable directly. There is a workaround which involves kind of creating an equivalent fish variable to the Python variable and then getting the history of the fish, but there's no direct way of getting it of a Python variable. There's also no way to use commands that take the name of a Python function, and there's also no inline Python in the same way that there's inline fish. So the Itasca module is a Python module which exposes the FLAC3D, 3DEC, and PFC types. And the Itasca module is the main way to go about connecting to the software itself from within Python. These types are represented within the module as classes. And so you can create instances of them through objects to allow you to interact with the module. And this covers all of the types, everything from zones to grid points to structural elements and so forth. The module also contains static functions to perform different methods. So there's two main interfaces for interacting with the module. And I'll explain later kind of the main differences between the interfaces and the advantages and disadvantages of using each. The two main interfaces are an object-oriented approach, looking at the different instances of the classes, as well as an array-oriented approach, which allows for the integration of NumPy for vastly faster computation times. So there's also, as stated, several powerful general purpose functions within the module. And these range from everything from allowing you to evaluate Itasca commands from Python, to getting and setting fish variables from Python and calling fish functions, to calling Python functions during a cycling sequence, as well as kind of stated priorly, detaching the Python state from the model itself to allow Python to kind of serve as this hierarching power. Since the Itasca module is a package, and using it within your Python code, you'll always have to import it as one of your kind of first lines. And typically, just as a nice way to abbreviate the code, it's kind of the standard to import the Itasca library as this IT shortening. And you'll see through kind of all the documentation and examples that's the syntax used to represent the Itasca library. So documentation for the Python connectivities can be found within the standard 3DEC and FLAC3D and PFC documentation. And I included some links here, but the main thing to note is that the documentation can be found when you go to the standard Itasca documentation, either through the web browser or through the software itself. Once you go to your software-specific documentation, within the tree itself, the Python documentation can be found under Python scripting and Python scripting. And one thing to note is during today's lesson, I'll be going over several different examples of how you can use the Python connectivities within the software. And if you want to come back to these examples, you can either do so through the slides, but also most of the examples are available within the documentation itself. So the documentation kind of presents the Python documentation in the form of these generated lists. And so this provides descriptions of the variables needed to pass as parameters to each function, what each function returns, as well as a description of what each function does. So for example, this first function add save variable takes the variable name as a string and returns nothing. And this is just then a short description of what that function actually does. So that's one way you can go about trying to, or what you can go about figuring out what different functions need or pass as parameters, as well as what's available within the Itasca module. The other option is to use the inline help available in the IPython console. So as kind of shown before, you can use the readily available help function and pass to it either a function, a module, or a class, and it will then output to the console a list or a string of what the documentation actually is, describing what the functionality does. So it's also possible within the Itasca module to issue commands from Python. So this is done via the command function, and it takes a string and then issues that command. So for example, this code, once executed, will issue the zone create brick command. Multiple commands can also be issued at once by using multi-line strings. So in this example then, 5 commands would be issued at once after this function was called. So as kind of an interlude though, it can be very powerful when calling commands within Python to create command templates with string formatting. So as an explanation of what string formatting is, you can represent kind of this sentence or this phrase, my name is Sasha, within Python just as an entire string. However, if you wanted to make the name of the person more variable, you can use string formatting to base it off of some variables within your Python script. How this is done is using the curly bracket notation and the format command. So what this function does is it inputs this variable that you pass in as a parameter to the curly brackets within the string. And one thing to note is that you can do this for as many curly brackets and variables within a string as you want. You can also assign names to each of the curly bracket parameters by inputting a string of the variable name within the curly bracket itself. So what this then allows you to do is, rather than simply passing in the parameters in the order that there are curly brackets, you can instead use keyword arguments and pass that into the format function. And so both of these lines of code would execute to return the exact same string as the first line. You can also use string formatting to format the output of numerical values. So, for example, you can format numbers to a certain decimal point or to return an exponential format. How this is done then is using a colon and a dot followed by a certain specific command within a string. So what this kind of formulates to is the 2 here within the string formulates to the number of decimals after the point which should be displayed. And the F formulates to the format that the number should be displayed as. So in this case, a float. If the same string was called with an E instead of the F, then it would be formatted as an exponential rather than a float. And this just allows for kind of easy output for when you have numerical values, since Python might be rounding these to up to 16 digits, and it might be very difficult to kind of see and visualize that when you're outputting it. However, the main power of string formatting is to create templates for your commands, which you can then vary based off of input. So this is an example where some brick data is loaded in from a file within the workspace. And then a command template is created, which first creates a brick, assigns some properties, and then assigns further properties based off of the inputted values. And so after those values are gotten from the loaded in data, you can then create commands based off of that template. And so in this case, the template is only used once to format the command for the specific density Young modulus and Poisson's modulus get loaded in from the data. But if you instead had a text file which contained 1,000 data points, you could then iterate over this command template, and it just makes formulating commands significantly easier. So it's also possible within Python to get and set fish variables. So in order to do so, you firstly have to call the command fish.set, and then the name of the variable as a string and the value of the variable. Now, this first command here is something which I'll come back to, but basically what it does is it simply detaches the Python state from the model. So one thing to note about the set function, though, is that if there's already an existing variable within your fish workspace called x, it will overwrite the value of the existing variable. Else it will simply create a new variable. You can also get values of variables via calling the fish.get function, and once again passing the name of the variable as a string. It will then return to you the value of the variable, or throw an error which could potentially crash your program if the variable doesn't exist within the workspace. It's also possible to call fish functions from within Python. This is done by doing the fish.callFunction command. And once again, you pass in the name of the function as a string, and the function call in Python will automatically return the results, if any, of the returned value from the fish function. It's also possible to pass arguments to this function by declaring the arguments as a tuple of whatever argument values you want, be it objects, strings, custom data types, and then by passing the arguments as a secondary parameter to the call function method. Python callbacks can also be set up so as to be called during the cycling sequence. So in this code example, a callback is set up which simply increments the value of I and prints in Python callback function. In order to add a callback function to the cycling sequence, you simply call the set callback command, giving the name of the callback as a string and passing in the index of where you want the callback to be called in the cycling sequence. And so, as we kind of learned before, within Python, -1 indicates the start of a list or of an array. And so this simply tells Python to call the callback named myCallback as the first thing within the cycle sequence. We then issue a command to the Itasca module, telling it to cycle 3 times. And then we output the Python callback function was called, how many times it was called, formatting it with the I variable. You can also remove callbacks by the remove callback function. Once again, specifying the name of the callback as a string and then the index of the callback within the cycle sequence. And so if the output generated by this code sequence is in Python callback function 3 times, since in the first portion of the code, it's cycled 3 times, and thus the callback is called 3 times. And we can see that before we removed the callback, it was called 3 times, and after we removed it, it was called 0 times. You can also detach the Python state from the model itself. One way to do this is by adding a specific save variable and thus excluding it from the reset. So, for example, in this example, you use the add save variable function to add a specific variable, passing its name as a string to the parameter, and this will then have the variable saved when the model is saved or reset. You can also remove save variables once you've added them by calling the remove save variable function, or you can remove all save variables through the usage of the clear save variable function. Now we come back to this kind of command that we saw before. So this command is one that completely detaches the Python state as a whole. Rather than specific variables within your Python workspace, it detaches everything you have created within the Python workspace as of now, as well as any future variables and functions you create. The standard when programming kind of within Python, within the Itasca software, is to always include this command. It's as the very first thing you call after importing the Itasca module. And as a kind of reason and justification of that, let's kind of look at a little code example. So within this example, we import the Itasca module as normal, and then we call command to reset up the model so that we can then go about creating whatever Python things we want to do. However, one thing to note is that since the Python state is attached to the model by default, resetting the model will also reset the Python workspace. This will mean that IT, which is simply a variable, will no longer exist within the workspace. So then if we try to call a command such as creating a brick, this will then throw an error and cause our program to crash. That's why by default, we typically always detach the Python state completely from the model. That way, if we create a new model or restore a previous state, we're not going to accidentally wipe the Python workspace and throw any errors. So the connectivities to the Itasca software. can be represented as kind of a tree of the different levels of things which you can access. So at the top is the Itasca module itself. This is the primary and only way you can connect to the software and allows for all the power within there. Now, within that module, there are several different sub-modules which each represent a specific type or other sorts of utility functionalities. So as just kind of two examples of some modules available, one is the Itasca.zone submodule, and its kind of equivalent in the array-oriented interface is the Itasca.zone array module. Now, one thing to note is that for all of the types within the software, their kind of equivalent submodules which represent them are all called in this kind of same way. So grid points, for example, are called as an Itasca.gridpoint, and its array interface is Itasca.gridpointArray. Now, within each of these submodules are different functionalities. So as just some examples, within the Itasca.zone function, or Itasca.zone submodule, are functions to get a count of all of these zones within a model, or to find a specific zone object based off of a zone ID. Equivalently, within the zone array submodule, there are functions to return the IDs of all of the zones, as well as the positions or properties of all of the zones. Now, within the object-oriented submodules, there are also classes which represent the equivalent type within the software. So for example, in the zone submodule, it also contains a zone class. And it's important to note that the naming convention here is the submodule is called lowercase z zone, and the class is called uppercase z zone. And this is kind of important to note if you're working in the object-oriented interface, so that you don't accidentally try to call some object functions on the actual submodule itself. And once again, this naming convention is consistent for other types, such as contacts or grid points. Now, within each class is then specific class functions, which can then return the position or the properties of that specific zone. So, to further highlight kind of the fundamental differences between the object-oriented interface and the array interface, in the object-oriented interface, you always are interacting with one object at a time, one specific instance of a zone class. And that object then provides connectivities for the ID of that zone, the position of that zone, and the properties of that zone. Within the array interface, however, you're interacting with all of the zones at once. So those prior functions, rather than simply returning the ID or position or properties of a single zone, return the IDs of all of the zones within the model as an array. So rather than interacting with a single object at a time, you're interacting with all of them at once. Now, while the object-oriented interface then is kind of easier conceptually, the array interface allows for NumPy integration, which then allows for significantly faster and more efficient code. So if we kind of go back to those speeds we were looking at before, these kind of Python and NumPy speeds are, you can also really think of them as the differences between the object-oriented interface speeds and the array interface speeds. You're only ever really able to get up to these extremely fast and efficient codes with the NumPy through the array interface, because that allows you to access and modify and get information from all zones or all types within a model at once, rather than specifically looking at one type or one object at a time and doing that for how many zones you might have. So the caveat to that, though, of course, is that the array interface code tends to then be more complex and can be kind of harder to conceptualize and wrap your head around at first. However, it's definitely beneficial to try to program in that manner in the long term, since it is vastly faster and more efficient than the object interface. So moving on then, we'll begin to cover firstly the object-oriented interface, so what's the actual code to interact via there, and then move on to the array interface and what's the code to actually interact through there. To kind of go through the object-oriented interface, we're going to kind of go through different classes and objects available for the separate types and look at the functionalities available within those submodules and within those classes. So firstly, we're going to go over zones. And when working with zones within the software, you can firstly get a count of all of the zones within your module by calling zone.count, which is a function within the submodule. So this returns a count of all of the zones which you have in your module. You can also find a specific zone via calling the find function, which then returns a zone object based off of the zone's ID. And so printing this zone, we can see that this is kind of the typical format that Python prints objects as. We can see that this Z variable is holding a zone object, and this is simply in relation to the memory location. You don't have to worry about it. But we can see that after finding a zone with ID 1, it returns the zone that has ID 1. Zone objects also have their own separate properties and functionalities. So one of these is the position function, which returns the position of the object as a vector 3. And a vector 3 is just kind of a specific data type, which is kind of interacts basically as you would expect to, and simply represents an XYZ variable. And so we can see that this zone is positioned at 0.5, 0.5, 0.5 in the XYZ dimensionalities. Now, you can also return via the object interface a list of all of the zones. And from this, you can then iterate over all the zones, once again, kind of going through each zone at once. And you can then get the zone's volume by calling the vol function in order to get, for example, a summation of all the volumes within your model. You can also use the near function within the submodule to find the zone which is nearest to a specific point. So, for example, after calling this, it returns the zone whose position is 4.5, 4.5, 4.5, which within this model, is the closest zone to the 555 point. Now, zones can also have certain properties, and these properties can be accessed via the props function on a specific zone object. This then returns a dictionary with strings of the property name mapping to the value of that property. These properties can be then modified via the setProp function, passing in the name of the variable as passing the name of the variable as a string and the new value. So for example, here we reset the value of bulk from 8e to the 9th to 8.5e to the 9th. So another object available within the Itasca module that represents the ball type. So very similarly to the zone type, the ball submodule contains a function to return the count of all the balls within a model, as well as find a specific ball from an ID. The ball object, though, has some specific properties. For example, you can get the radius of a certain ball, which then allows you to sum all of the radiuses, all the radii within a model via, once again, the usage of the list function available within the submodule. Balls also allow you to access their contacts, and that's done via the .contacts function. Now, this returns a list of contact objects, which represents all the contacts that a ball has. And for example, you can then use the len function to get the number of contacts that a ball has. The contacts then have specific information related to them. And so for example, here we output all of the contacts IDs and positions. You can also then access, since the contact function simply returns a list, you can access a specific contact by indexing into it. You can then get information such as the global force on that from that contact, as well as all contact properties, which once again returns as a dictionary mapping the strings of the variables to the actual values itself. So grid points as well can be represented as a submodule and a class within the Python connectivities. Once again, the submodule has very similar functionalities and allows you to get counts or find an object based off of its ID or its position being near to a certain point. Grid points as well have specific parameters based off of them, such as a mass gravity, which you can once again use the list function to iterate over all of the grid points and perform some form of calculations or access information based off of. And just as kind of one final example, you can also represent structural elements within the Python connectivities. Now, one thing to note with structural elements is that within the Python connectivities, there are several different types of structural elements which are represented. And in order to determine which type the structural element is, you have to use the type functionality. So in this example, we are checking whether these are a variable struct elem, which is representing a structural element, is a shell. And so this is just a Boolean expression which will return true if the structural element is a shell. And so you can then use this to differentiate your structural elements between cables, beams, or all other sorts. And once again, there are kind of equivalent functionalities across all of the submodules for getting a list of the objects or accessing specific information such as its IDs or its young modulus and so forth. So it's kind of relating off of that. There are several commonalities across all of the objects and all of the submodules available through the submodule interface. So for example, there are some of the common functions across submodules are a count function, which returns the count of all of that type, a find function, which takes the ID of a type and returns an object of that and returns the equivalent object, a near function, which returns the object nearest to a specific point, and a list function, which returns a list of all of the elements of that type. And there's more kind of common functions, and once again, kind of the best way to go about seeing what is available, because there is so much connectivity, is to do so through the actual Itasca documentation available within the software or within kind of your web browser, accessing it through there. There's also common functionalities across objects. For example, getting the position of an object, its property values, setting the property value with the string of the property and a new value, as well as setting an extra variable with the index of that variable, as well as that variable itself. And just kind of as an example of that last one, here is an example where a zone is found near to a specific point, and then two extra variables are set using the set extra command. Those variables are then accessed by the .extra command, passing the index of those variables in as a parameter. And the output of that is then the different variables. So then moving on to the array interface. So as kind of stated previously, the array interface tend to be kind of more complex to think about, but generally tends to result in neater code as well as much more efficient and faster code. Within this example is kind of the typical starting point is to import your various libraries. So once again, similarly to how Itasca is shorted to IT as just kind of a general code syntax, your zone arrays and grid point arrays, which are the equivalent to the zone and grid point submodules for the array interface, are typically shortened to ZA and GPA, which just kind of saves you the hassle of always writing zone array and grid point array whenever you want to access some functions. And just kind of once again reiterating that you're always going to want to tend to detach the Python state completely before you do anything else within your code. So as was kind of shown before, within the array interface, accessing the position of all the zones doesn't return kind of the position of a single zone, but returns the position of every single zone within your model. And these ellipses are just kind of used to shorten it, because else this would continue all the way off the page for all thousands of zones. And so these zones are represented as a NumPy array by default. And you can see that each array has an X, a Y, and a Z position. And then this is actually a NumPy array containing other NumPy arrays. And this can be verified by assigning a variable to the return of the position function, and then by checking its type. Now, based off of that, we could then start to do powerful things based off of the NumPy array functionalities. So for example, we can get the shape of our NumPy array and verify that it contains the same number of elements within itself as the number of zones within our model. So the NumPy array is a 1000 by 3 matrix, since there's 1000 zones and each has 3 positional elements. You can also then create separate NumPy arrays of each X position, Y position, and Z position. And that's done by using the transpose function available on NumPy arrays, which is simply denoted by .t. So we can then see that our X variable is a NumPy array containing all 1000 X positions of the zone objects. And this is kind of useful to break up our positions into these different things, because then it allows us to begin applying range logic as simply NumPy array masks. So for example, if we access all the zones which have a value of Z greater than 5, this will return a NumPy mask where each index has an element evaluated to whether its Z variable is greater than 5 or not. So we can then begin to do some very powerful things with the range logic within NumPy. So for example, we can get the summation and the number of all of the upper zones within our model by assigning a NumPy array equal to the return of the last slide, so where all variables have a Z variable greater than 5, and then within NumPy, calling the sum function simply returns how many entries are true. So this will return 500, since 500 zones have a Z variable greater than 5. So we can then begin to use range logic within this by, for example, creating an array which has the same shape as X, and then by specifying that all of the upper zones have a modulus of 1.2 e to the 10, and all of the lower zones, which are simply not the upper zones, have a different modulus. We can use the setPropScalar function available within the zone array to then set the property youngs to our NumPy array. And so this is just kind of an example of the power of working with the array interface rather than the object interface. In the object interface, in order to accomplish this, you would have to iterate over every single object, check if its z variable is greater than 5, and if so, assign it a Young's modulus of 1.2, else assign it a modulus of 1.6. In contrast, in the array interface, we can simply say that we want our mask to be the z variable being greater than 5, and then apply that all at once across all the zones, which allows for vastly more efficient and faster code. Now, you can also do a similar thing with, instead of range logic, with group logic. So groups can be accessed, read, and modified from within the Python connectivities within the zone array submodule. So for example, the ingroup command can be used to return an array, evaluating to whether each specific object is within that group or not. So using the sum function again, we can then return a variable of how many zones are within a specific group. We can then further refine this via the use of different NumPy operations to, for example, get all of the corners. So in this case, we are simply creating a new mask, where all of the x variables, y variables, and z variables have to be less than 3. And this reduce function is simply applying the logical AND within the NumPy array functionality to all of that. So it has to be x is less than 3, and y is less than 3, and z is less than 3. The grouping of that is then set by the setGroup function within the zone array, that each function within the corner mask, which evaluates a true, has the group corner and geometry. So then the ingroup functionality can be used to output how many zones are within an actual corner group. And so that then actually brings us to the end of this presentation. That pretty much covers the object-oriented interface and the array interface of how you can interact with the Python connectivities towards the Itasca software.